In this video, we're going to talk about the reduction of alkynes. So just like with alkenes, we can use catalytic hydrogenation to add hydrogens to our pi bonds. And in this case, it's sort of a two-step process. We first create the cis alkene, because just like with catalytic hydrogenation of alkenes, the hydrogens add via syn addition, so the hydrogens add to the same side, and then it is further reduced to the alkane. Now, if we just use hydrogen with a metal catalyst, we'll go directly from the alkyne to the alkane. But if we want to stop and just form the alkene, we can use what's called a poison catalyst. Two examples of poison catalysts are Lindlar's catalyst and P2, which is a nickel-boron complex. And you don't need to memorize what Lindlar's catalyst is, but these are the reagents that we would use for Lindlar's catalyst. And so that stops the hydrogenation at the cis alkene. So the way a poison catalyst works is that it does catalyze the first step, so the hydrogenation to form the alkene, but then it doesn't catalyze the second step. And so that's why it stops at the alkene intermediate instead of reducing it all the way to the alkane. Now, a poison catalyst will produce the cis alkene. If we wanted to produce the trans alkene, we could use a reaction called dissolving metal reduction. And that's where we take sodium metal dissolved in ammonia. In that case, the reduction stops at the alkene, but we get the trans alkene because the reaction proceeds by anti-addition, as opposed to the poison catalyst or regular catalytic reduction that follows syn addition of the hydrogens. I think it's worthwhile to talk about the mechanism for dissolving metal reduction. And so I'm actually going to zoom in a little bit because this slide is a little bit small. So we have the sodium metal, and if you recall, sodium has one valence electron, and so the sodium donates that electron. And if you notice, because we're only dealing with a single electron, we use a hooked arrow, right, or just a half arrow. And then these other half arrows represent the movement of just a single electron. So from the pi bond, one of the electrons pairs with the electron from the sodium to make a lone pair on this carbon, and then the other electron from the pi bond moves to the other carbon, and we form a radical, right? We have an unpaired electron. The next step is a proton transfer. So our electron lone pair on this carbon takes a hydrogen from the ammonia. And then in the final step, we get, actually not the final step yet, we get another sodium donating another single electron, right, that pairs up this electron now. And then now in the final step, we get another proton transfer from an ammonia to complete the reduction. And so the reason this mechanism prefers the anti-addition is because in this intermediate, when we form the lone pair and the single unpaired electron, right, these electrons are going to repel each other, so they don't want to be in a cis configuration. They prefer the trans configuration where they can get farther away, and so this is why we get anti-addition in this dissolving metal reduction. Okay, so to sum up the reactions that we learned in this video, we can take the alkyne all the way to the alkane by using hydrogen and a metal catalyst. If I want to stop at the alkene, I can either use a poison catalyst like Lindlar's catalyst to give the cis alkene, or I can use sodium dissolved in liquid ammonia to give the trans alkene. And then, as we learned from the last chapter, if I want to take the alkenes to the alkane, then I can just use hydrogen with a metal catalyst.